Great to see you all, cast of thousands. We're hard at it. We're very lucky to have a combination of speakers here today. Some are the old timers like me. Others are newbies to this operation. One of the newbies is David Hoyle, who for years worked with systems and machinery in the oil industry. And somehow or other, when he retired, lives in Phippsburg, Maine, and he's close to some tide mills there. What we assigned him to do is what we tried for many of our conferences, that is to look around the world and see what's happening in ocean energy, tidal activity. You will be impressed with what's happening, and you'll be impressed with David Hoyle. Welcome, David.
Thank you, Bud. Thank you, Bud. So maybe a little further introduction. So as Bud said, I live in Phippsburg. I moved permanently to Phippsburg just over a year ago. And I was able to take Bud's tide mill class last fall. I thoroughly enjoyed that, and I learned there about the history of tide mills, the historical part. And where does my interest in the new technology come from? So as Bud mentioned, I left, if you all remember last year when the price of oil went negative for a little while, last spring. That's right around when I exited the oil industry. And I have two millennial sons, two adult sons. They've been very clear with me that I needed to atone for those 35 years of fossil fuel sins. So hence my interest in renewable energy and specifically ocean energy. So just to be clear, right, I'm sharing with you something that I'm learning about and becoming passionate about, not something that I'm an expert in. Okay, so I'm going to talk to you today about the latest and greatest in tidal energy technology, and I won't limit it just to tidal. We'll also talk a little bit about wave energy and wind energy as well. Here's the overview of the presentation. We'll have a couple of working questions, but it's really what is tidal energy's role in the overall renewable energy mix? Is it anecdotal, or is it bigger than that? I think to understand that, we need to understand how much tidal energy is out there to harvest, and we'll also look at wave energy and wind energy. So how much is available to go after? We'll then look at the types of technology, the types of systems that can be used to harvest tidal energy and also wave energy. And then I'll start looking at a few examples and applications. So I thought I would start with something very close to home, close to what the people interested in the history of tide mills are familiar with. So we'll look at a little bay in Maine, and we'll look at, instead of mechanical power to saw lumber or grind grain, we'll look at generating electricity, how much power we might get. I'll then turn toward what are called maritime applications. This is something I just learned about recently, but these are applications that you could think of as a bridge, kind of smaller scale applications. It could be a bridge toward larger scale, utility scale applications. So those are maritime applications. And then we'll look at some examples of companies working from a smaller scale towards the larger scale of utility applications. So tidal energy, the anecdotes, right? What's not to like? I'd love to charge my Tesla at a tidal power station and tool down to the pub to eat oysters and drink scotch, all produced with tidal energy. Okay, it's fun, but can we get beyond the anecdotes? So where does tidal energy fit? Can it compete with the big boys, right? I think we all understand that wind and solar are going to be the big players in renewable energy, certainly on land. And we'll see that offshore wind is going to be big. So where does tidal fit? Where does wave fit in that picture? Will it be a big player, or will it rather focus on some niche, smaller applications? And experts have told me, hey, niche isn't a bad word. It's a good place to start. Where does wave energy fit in as well? So this is from the National Renewable Energy Laboratory. This is the United States ocean energy potential. So let me unpack this a little bit. The numbers that you see here are in terawatt hours per year. So a terawatt hour is 1 trillion watt hours of energy. You think of your electric bill, you pay for kilowatt hours. A terawatt hour is 1 billion kilowatt hours. So I just told you that one big number is a multiplication of 2 other big numbers. Maybe it helps to look at the numbers on the bottom. We'll do that in a minute. So what we're looking at here in the color coding, wave, light blue, tidal in orange. There's also ocean current. I won't talk much about that, but that would mean that we were trying to harness the Gulf Stream, for example. There's also thermal energy and river energy that make up this total. The total at 2,300 terawatt hours, that's the total of potential of all of those ocean energies. That would be about half of the total electricity need of the whole United States, something like 4,000 terawatt hours per year of energy. But I draw your attention to the table at the bottom, and here we have wave and tidal, the wave and tidal components. So you can see tidal, 220 terawatt hours per year, maybe 21 million homes, roughly 5% of the US power needs. So not enormous, but these are still big numbers. Wave is important to pay attention to, right? It's 6 or 7 times bigger than tidal, enough for an awful lot of homes, and could cover 1/3 of the energy needs of the whole country. A few other things to notice: most of this US tidal potential is in Alaska, something like 95% of it. And the US tidal potential is something like 3% of the world potential. So it's really small, and that's why we'll take a look over at the UK, where there's a very big potential. Okay, so this is the kind of the raw physics. This is how much energy is out there to be harvested theoretically. Now I'm going to turn over to wind for comparison, right? We kind of all know that wind is going to be a big boy. So the wind potential for the US, 7,200 terawatt hours per year. So that's 33 times the wave potential, the tidal potential, sorry, 5 times the wave potential. So wind is absolutely huge. And wind is moving fast. So this is a map, that's the east coast of the United States, the west coast, and then Hawaii in the upper left. This is a project pipeline. So these are 35 gigawatts, 35 billion watts. This is now power. So 35 gigawatts, that's something like 15 to 20 million homes that could be powered. And okay, this is where it's interesting. It's very hard to keep abreast of this. So a month or so ago, we saw the Biden administration had announced a plan, 30 gigawatts implemented by 2030, part of the big green energy plan. The middle of last week, Interior Secretary Deborah Haaland said, I'm going to get after this. I'm going to turn all of these sort of pie in the sky projects into real leases that developers can bid on and start developing offshore wind farms. Today's news in the New York Times said the whole clean energy thing may get scrubbed out of these bills that the Biden administration is trying to pass. So we've got to keep after this on almost a daily basis. I think the point here is wind turbine technology is very mature, certainly on land. To implement it offshore or far offshore, we need floating platforms, and there is development work needed in those. There's very interesting work going on with the University of Maine. There's the project number 1 up there at the top is the New England Aquaventus project, which is developing low-cost platforms for offshore wind turbines. So the wind industry can't afford an oil industry type of platform. And offshore wind is supposed to cost about the same as we're all used to paying for our electricity. So, you know, this is kind of the one to beat. And I looked at this and I got a bit discouraged about where was tidal energy going to fit in. But the experts say, well, not so fast. If you're going to deal with renewables like wind is highly variable. Yeah, you're going to start injecting this into the power grid. It's an unknown quantity from day to day. Tide is, as you all know, is highly predictable, right? We know the height of the tide and the period of the tide is as far out as we want to do the calculations. So bringing that predictable energy into the mix is very important. But of course, wind is, in terms of technology maturity, wind is much more mature. Tidal is up and coming, wave quite immature. So now I'll talk about types of converters, tidal energy generators, if you will. So let's start in the middle with what I'm calling a tidal barrage. That's just a cross section through any sort of generic dam, and it's got a turbine in it. Kind of looks like a small wind turbine, right? So this is really more appropriately called tidal range, and this is what the whole Tide Mill Institute is about. This is what 19th century tide mills were about. What generates the power is the range of the tide, the height of the tide, and of course, the difference in the height of water across a dam, right? That's how we're generating the power. That dam can be a short dam across a small bay. It can be a long tidal dam or fence enclosing a man-made tidal lagoon to generate electricity. In the whole world, there were only really two big tidal barrage projects, one in France, one in Korea, each generating about 250 megawatts. So what the industry is really tending towards is what we see toward the left of the slide, tidal current. So this says that as the tides ebb and flow offshore, they generate currents. This is what we have in the US, offshore Alaska, certainly offshore UK. And to harness that energy, that movement of the water, we can use turbines that can look very much like a wind turbine. We'll see other ones that look quite different from that. They can be anchored on the sea floor, or they can be mounted on a floating body, which would be tethered to the sea floor. So we'll see examples of those. Here on the right, very fun technology. This is a tidal kite. I'll come back to it in my last slide. And this is technology intended for use when the water flow, the tidal flow, isn't very fast, but we still want to generate power. I'm going to just show a few examples of wave energy converters. So on the left, these are called point absorbers. So what you have, the yellow objects are buoys. These can be quite large, 30 feet in diameter. They're riding up and down with the passing waves. And that up and down motion is actuating a generator, in this case, a linear generator. What's being shown here are magnets moving inside of electric coils. When you move a magnet in a coil, you generate electricity. So you can imagine a whole farm of these devices offshore generating power from the waves. On the right, this is a famous technology that I think didn't really go very far. So this is the Palamas system. I think it was called the Palamas Sea Snake. So it's something like a large train or snake that is floating on the waves. As the waves pass the device, it causes joints to flex. The flexure of those joints moves hydraulic rams, which in turn drive generators to generate electricity. And you can see for those in the room in the lower right, you could have a whole farm of these machines as well. And here they're talking about generating power for 20,000 homes. So this was aimed at utility scale. And I'll show one more example. Let's see if I can play a little video for you. Bud provided this. So here, imagine now that we're close to shore, just on the shore, on a jetty, and we're very, very near the shore. So here we have buoys, again, riding the waves. The buoys are connected They're called floats here, turning the kinetic energy of the waves into electrical energy through pivot arms driving this hydraulic system, which is again driving a generator. And they like to show that those can be raised out of the water when a big storm is coming, which of course happens fairly often these days. Okay, so those are just a few examples of technologies. It's impossible to be exhaustive in that. There are many more, and I encourage you to look at those. So what I wanted to talk about now was a little sort of case study. I'm calling this the fictional case study, just in case I didn't want to anger any of my neighbors in Phippsburg. This is not going to happen, right, in the basin. But so the basin is a little kind of wonderful little body of water, a little bay on the west side of Phippsburg. It's about 2 miles south of where I live. So I've been coming to Maine for many, many years vacationing. And as an engineer, I would look at these little bays and I would say, well, how much power could you generate if you harvested that tide? It's something my dad and I would talk about. And I thought you had to start looking immediately at water wheels and things like that, but you don't. In fact, the calculation is fairly simple. So this is the first thing I've learned that I wanted to share with you. So what I've done, this is a Google Earth view of the basin. At the bottom, you see what I've labeled old dam. So that was an old tide mill, probably to grind grain or saw lumber. It impounded a couple of acres of the basin to generate mechanical power. So what I'm trying to do, I'm very greedy. I want to impound the entire basin with a new dam over here. So how do we calculate the amount of electricity we might be able to generate with such a system? So there's a simple formula to do this. This constant at the beginning has to do with gravity, the density of seawater, and the tidal period. But all we need to know really is A is the area of our impounded pond, and H is the tidal range, the tidal height. So this is fun. I encourage all of you to choose a small bay, go in Google Earth, trace the perimeter, and you get the area. And of course, you can find the tidal height easily. So here we've got about 145 acres. I'm using a 9-foot tide. And we see that we can generate something like 400 kilowatts. So we could power maybe 200 to 300 homes. I also put that in terms of maybe 10 acres of solar panels. Probably would prefer the solar panels, would be my conclusion, but I don't want to get ahead of myself. So we could generate that much power. Now, of course, we'd need a dam. Now, do we have to make a concrete dam or a stone dam? I think it might be interesting to do something novel. So this is from Professor Gorloff, that some of you may have heard of, and we'll see his turbine technology coming up in a few minutes. But here he's proposed, this is from a patent, and he's proposing a flexible dam. So this is a dam in the upper picture here. It's suspended on a cable. There are also floats on that cable. It's anchored to the seabed. And then he's got a power generation station over here on the left. So for our purposes, we need one of these about 220 feet long. And we're also, we need to allow fishing boats and pleasure boats to pass freely. Again, I have to think of my neighbors. And we have to allow fish and marine mammals to pass freely as well. So maybe this is a technology we could use. Now you can see he's showing a boat. He's showing that the dam can be lowered here in the lower right of the slide, and then a boat could pass through. I ask you to imagine trying to lower the dam when there were 9 feet of tide across it. That would be interesting. Okay, what would the power generation look like as a function of time? So I've done just a little mathematical modeling. What I'm doing here is comparing what we know as tide mill historians, the kind of one-way power, outflow power, right? So in an old tide mill, water came into the mill pond through the gates closed, we waited a little bit, and then we started sawing lumber or grinding grain. So that's the That's what I'm showing with the red curve. In fact, I'm starting my generators here about 1 hour after high tide. Power peaks up and comes back down. And you could see, as we all know, we could saw lumber for 4 to 6 hours or something like that. But with turbines, now this has been done, but we'll tell you about the Bodenham mill, which had a two-way water wheel, but it wasn't very common. But with modern turbines, we can use two-way power, and I'm showing that here in the blue curve. So we can generate power from the water flowing out as well as from the water flowing in over the 12.5-hour tidal period. And I think if you calibrate your eyeballs, you can see that there's more blue on the slide than there is red. Yeah, there's about 50% more. So that means we've generated about 50% more energy over the tidal period using two-way power. This is kind of the second thing that I learned in looking at this kind of technology. Now, is this something anybody would really want to do? And I've spoken with various experts, Gail Stidlewski, who's a fish biologist. The current trend is more, let's remove dams from rivers and bodies of water than build new ones. Yeah. So I'm not sure there's a big appetite for that. Todd Grisey also said the same thing. Fish need to get into these small bays to spawn and to mature. There are going to be siting challenges, regulatory hurdles. We've just seen that the Maine Audubon has published a siting tool for renewable energy, something I'm going to learn a little bit more about. We all know about not in my backyard. I think this would turn into not in my bay, thank you. I can just imagine my neighbors, the lobstermen and the pleasure boaters, if we said we wanted to dam up one of these little bays. And as I mentioned, the tidal energy companies are more focused on these open flow tidal current turbines than on putting turbines in dams. All of this said, Trey Taylor of Verdant Power told me, well, never say never. If you're clever enough and you can overcome these obstacles in a good way, maybe you could do a tidal barrage system. Okay, so I'm going to turn to what I was calling maritime applications and kind of smaller applications, good places to start if you're a company that wants to get into the business of renewable energy. So a few examples I've highlighted at the lower left, desalination plant, and I'll show an example of that. Isolated power systems at the community scale. We'll see that in Alaska in a subsequent slide. Underwater vehicle charging. So very, very specific small scale applications. Why would this be, if I'm a company, why would this be interesting? Again, these are slides from the US Department of Energy. So one, these are markets that require smaller scale devices rather than big utility scale devices. And these are typically markets that are served by high cost fuels. So maybe I have to transport diesel to Alaska to a remote village to generate electricity, right? So those are the kinds of markets. And from the point of view of technology development, this can bring near-term revenue to a company. Start small, start in one specific area, and so that we can do our research and development at a smaller, more manageable scale. It's much easier to field a small prototype than a large one, much easier to find a test site for a smaller prototype. And as we get beyond prototyping, as we get into early commercial development, we can develop technologies, reduce costs. We need to have economies of scale, of quantity. We need to develop supply chains. Improving installation, operation, and maintenance. These are all things that have to be done to reduce costs, right? If tide and wave are going to compete with wind, they have a big learning curve that they have to go through. So that's why these are what I would call a kind of bridge applications. So here's an example. This is from a company called Resolute Marine. This is a diagram of a seawater desalination plant that they're going to implement in Cape Verde, the Cape Verde Islands off of Africa. So you can see on the right, there's some kind of oscillating wave energy converter, and that's pumping seawater into a treatment plant, and which then produces clean water for the local population. So I spoke with the president of Phippsburg, the president of Resolute, and he said, yeah, this is for us, this is near-term revenue. I can't get started by going after, you know, offshore wind off of the US. This is offshore wave. This is a good place for us to start. And you know, it's also serving a humanitarian need, I think, which is very nice. Okay, this is now Ocean Renewable Power. I think many of you have heard of or heard from ORPC. So this is a company based here, actually in Portland. This is a picture of their first commercial project in a river in Igiagig. I challenge you to pronounce that, Igiagig, Alaska. And this is their first commercial implementation. So this is Native American population that are generating electricity by burning diesel fuel. So their cost is something like $1 per kilowatt hour, sort of 10 or 15 times what the rest of us pay for electricity. And you can see the goal is simple. Let's just reduce that by 90%, reduce that expense, and then reduce all of the greenhouse gases and other risks that poses. And show you, this is just a little video. This is their first unit in the Creechak River. And which you'll see the turbines are these are horizontal Gorloff turbines. So it looks like your old real lawnmower, yeah. And you can see that again, the advantage is the very low profile. So this has been run in the river in Alaska with ice flowing over the top of it. So you can see it's not going to be damaged by ice. It's not going to interfere with shipping. So I won't go into all the details here, but now we're on this this story of how do we go from the one-off to building multiple units. So ORPC has identified a whole host of opportunities in the Americas, from Alaska, Canada, down as far as Patagonia. These are all these kind of remote locations where electricity is very expensive, right? Probably generated by diesel and other means. And you know, they see this as their ticket. You know, I spoke with John Ferland, the president, and he just said, we've got to stop building these things one by one, right? We've got to get after it. We've got to reduce the cost, develop the supply chain, et cetera, work the bugs out. So let's look at their technology a little bit. So what I've been talking about, the unit that we've looked at was the RivGen on the just to the left of center here, highlighted in green. So you know, RIV for river, 40 to 80 kilowatts remote communities. But I draw your attention to the Optimor shown here on the right. The scale is much bigger. Now we're talking 1 to 2 megawatts, 1 to 2 million watts of power. How are we going to get this developed? You know, this is a big leap in technology. Oh, under development in partnership with the European Union, because the European Union is willing to invest money in developing these kinds of technologies. So, and I think ORPC worked with Ireland to do this, right? So this is what we would then use to take megawatts of power out of the tides. So that's ORPC. This is Verdant Power. Verdant is based in New York City. Their turbine looks much more classical, right? It's kind of a scaled down wind turbine. Their initial units are 5 meters, 15, 16 feet in diameter. And you can see 3 of them here mounted on a triangular frame. This has been deployed for some time in the East River off of Roosevelt Island in New York City. And here the East River is in fact tidal with a reversing flow. So this is actual tidal power generation, and it's been connected to the grid and producing power. Here speaking as an engineer and engineering project manager, ORPC and Verdant are really doing what I would call the heavy engineering lifting. You know, it's one thing to field prototypes and that's all fine, but let's put in a system, let's go through 5 generations of the technology, right? And then let's bring in an independent body who's going to make measurements on the technology while my hands are off of it. So they brought in the European Marine Energy Center. We'll revisit them later when we talk about the orbital technology. And they made measurements of the power output and the availability of the system. So this is the hard work of developing a new product. And Verdant told me that they've achieved technology readiness of 8 out of 9. So technology readiness level is taken from NASA. 8 out of 9 means that if we're fueling a new rocket engine, it's been flight tested somewhere. Technology readiness level 9 means it's ready to go to Mars. Okay, so 8 out of 9 means that this technology is very well understood, well characterized, and they're ready to start scaling it up. So what are their plans? Well, let's go to the UK where that money is available again, interestingly. So they want to deploy 10 to 15 meter diameter turbines. That's 2 or 3 times as large as the prototypes. And do a 2 megawatt system by 2024, and then scale that up, expand that to 30 megawatts by the middle of the decade. They've identified 11 gigawatts, 11 billion watts of tidal potential around the UK. That's a big number. Again, leverage. I like his phrase was leverage that funding, then pivot back to the US. And they've identified a gigawatt of opportunity in New York State alone. And they have a long list of potential projects that they're looking at. So again, kind of starting small and working to scale up to utility scale. So let's go a little further afield with the last couple of examples. This is orbital power, and this is their so-called world's largest tidal generator. So what we see in the picture on the right is a top view of the actual unit, and we have a body, 2 wings, and there's a 1 megawatt turbine on each wing. This is its traveling configuration, and in the other pictures you see that the wings go down to put the turbines into the tidal flow to generate electricity. So you can see this is a huge unit. It must be 150 feet long, something like that. So they've got a lot of publicity, and they're now generating power at that European Marine Energy Center off of Scotland, sending power into the grid. And they're part of a very interesting demonstration project where some of that power will be used to generate clean hydrogen. Right? Clean hydrogen can then be a clean fuel for various purposes. And part of this is that they have what are called vanadium flow batteries. I have no idea what that means, but it sounds like new battery technology, which is used to smooth the power so that hydrogen generator sees a smooth flow of power from a tidal device. Very interesting. And, you know, they have a partnership with what's called the Perpetuous Tidal Energy Center off of the Isle of Wight, south of England, where they plan to generate 15 megawatts of power for the Isle of Wight by the middle of the decade. And I'm going to finish with, almost finish with this slide. This is Minesto. So this is the tidal kite. So if we look here, starting the lower right of the slide, we see it's kind of a big flying wing. And under the wing, we have a generator. You can see there's a propeller at the front and some kind of a tether arms. So again, in the upper right, we see that wing is going to fly in a figure-8 configuration in relatively slowly moving water, but the kite is flying very quickly relative to the water, and it's that high relative speed that's driving the generator. And we'll take a look at a little video here. So this is from a test site. The kite is tethered to that barge in the back, and we're going to see the kite emerge from the water as it does its figure-8 on the right and left of the slide. Pretty crazy. I wish I'd invented that. Okay, so all right. So those are my examples. I'm not gonna come back to my questions and try to answer them. I'm gonna leave that to the audience. And I think it's something, as I said earlier, that we need to do on a continuing basis. This is still somewhere in the future, as you can see, and how fast it all comes about really remains to be seen. To help us do that, I've started putting together a little digest on tidal and sometimes wave energy technology. You can find this on the Tide Mill Institute webpage. Here I really must thank Ron Kladensky, who turns my raw and ugly outputs into these very readable digests with live links, so you can read a little summary and then go read some very interesting articles on the technology. So I think it's something we just have to monitor continuously. I won't go into all the details here, but I've been able to have the privilege of speaking with a large number of experts, including some of our illustrious board members. And I'd like to thank everybody for what they've taught me about this technology, and I look forward to learning more. That's my presentation, and I'd be happy to take any questions if we have time.
Thank you very, very much. Go ahead and have at him for a couple of minutes, guys.
So I did this for Bud's class, last week, and Bud asked that people pepper me with questions. And they did, they really did. So if there's anything you'd like to know, if not.
After doing all your research, what's your, how optimistic are you that tidal energy will develop into a viable?
Cautiously optimistic, I think. I think it will certainly find some of those smaller scale applications. And again, today's news was maybe wind isn't going to move ahead as fast as planned. So very hard to say. But what I saw were people who are passionate about this and who are doing it also for good reasons, to serve remote populations who are desperate for low-cost energy. So it will find its place. There's another question?
Oh, it was just, for instance, with the kite, which is taken to the pond. Right now in the papers, the people who, the lobstermen are having problems. They're going to have to make through those lines, and just so we can save the whales or
Yes.
any other animal or fish. So how many of those would you have to put out?
You probably need a farm of them.
So we run into the same problem.
You would run into the same concern, and I think everybody will run into those concerns. The offshore wind people, one of the things they're working on is today they have to put the tethers way far out from the floating platforms. They want technology where they don't have to have so many cables covering so much of the seabed. So this will each project is going to will have its own environmental concerns to address, certainly.
Great. Thank you very, very much. Okay.